Next, universal law of gravitation. So in this one we consider every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them, and this force acts along the line joining the two particles here. So we are considered two particles A and B of masses m1 m2, a separate distance r in air. Okay, and the distance, the force of attraction between 1 and 2 is can be identified as F12 bar, and force by second one on first one you can write F21 bar. In general, the force of attraction between the two particles, this can be written as the F is proportional to the product of their masses and inversely proportional to the square of the distance between them. So you can combinedly written as F is proportional to m1 m2 by rs square, and F is equals to g m1 m2 by rs square. This is a gravitational force expression here we can use regularly, and where g is called universal gravitational constant. Universal gravitational constant. Gravitational constant. So it has a value. There is a constant value 6.67 into 10 power minus 11 Newton meter square per kg square. Okay. So next we can for the in vector form. So the formula, above formula we can read in terms of the vector notation here. So like we can consider the two particles again in the xy plane were taken. So we got again the particle A and particle B having masses m1 m2, and the position of the particle A is r1 bar and the position of the particle 2 is r2 bar. And we can find for the position between them, this can be written as r12 bar. The force of attraction between them F12 bar. The masses we can take m1 and m2. So the F12 bar can be written as the minus g m1 m2 by r12 mod whole square is equals to r12 cap. R12 cap is the vector, unit vector. Similarly, can write F21 bar is acting in opposite direction. We can substitute as minus g m1 m2 by r21 whole square into r21 cap. So that means F12 bar and F21 bar both are equal in magnitude but opposite in direction. That is, you can write F21 bar can be written as minus F21 bar, but in magnitude both are equal. Okay, If suppose R12 this can be written as R2 minus R1 bar, R2 bar minus R1 bar. R1 bar. So then you can write the F12 bar value or F21 bar in vector form. You can identify them as can be written as minus G M1 M2 by R12 whole cube into R12 bar. That is R12 value we are substituting here. So minus G M1 M2 by mod of R12 or R1 minus R2 R2 minus R1 whole cube into R2 minus R1. Okay, this is the R12 bar. So I'll consider the universal law of gravitation here. The main equation we have to remember here: gravitational force between the two bodies having considerable masses as G m1 m2 by r square, and in vector form, that is G value we have to remember here, that is 6.67 in 10 power minus 11, and in vector form it is can be taken as F12 bar can be written as minus G m1 m2 by r2 minus r1 whole cube and into r2 minus r1 bar. Now suppose we have the question like this: the particles m1 m2 m3 m4, there are 4 particles will be there. So there the diagram we got it here, and the distance between them is can be taken as r13. Force of attraction between also we can consider as F13, and in between 1 and 2 r12 bar, and force we can write F12 bar, and similarly you can identify them R14 bar and F14 bar, and you have to calculate the gravitational force on point mass m1. Gravitational force on point mass m1 is just a vector sum of the gravitational force exerted by m2, m3 and m4. That is, you can write F equals to G m1 m2 by r12 or r21 whole square into r21 cap plus G m1 m3 or m3 m1 by r31 whole square into r31 cap, and next plus can write G m4 m1 by r41 whole square into r41 cap. This is a vector sum of the 3 particles. Next, characteristics of gravitational forces here. The first one, it is always attractive in nature, nothing but if any two considerable masses here, we have only attractive force between them, and it is independent of the surrounding medium. So if you have 2 particles, the force between them does not depend upon the surrounding medium, and we draw the graph between the force of attraction and distance between the square of the distance between them is a rectangular hyperbola, because we know the statement here, f inversely proportional to the square of the distance between them. The shape we got it a rectangular hyperbola, and it creates the action and reaction pair. So action and a reaction pair, they will be act on two different bodies, not on the same body. And the fifth one, you got central force. Central force means it acts from center of the first body to the center of the second body. And next one is does not depend upon the properties of the medium, similar as the point number of 2 here. And is a conservative force. Conservative force is nothing but work done by it is independent of the path. Okay, and it is holds for point masses. It is hold for point masses, and these are the main properties here. And the next we can identify them. Shell theorem. So shell theorem means is a holospherical body we have to consider here, and we have to identify the attraction force by the holospherical body here. So what the statement of this one, can identify them. The force of attraction, the force of attraction between a hollow spherical shell, between hollow spherical shell, or you can call it a sphere, hollow spherical shell, or it can be called a sphere, of uniform density, of uniform density, and a point mass, and a point mass and a point mass situated outside situated outside is just as if the entire mass of the shell, if the entire mass of the shell were concentrated the center, or concentrated at the center. So now we can consider two cases here. The point mass will be inside and outside the spherical shell. What happened to the gravitational force? Okay, suppose you can consider the first one. The first case we have taken, the point mass is taken outside the spherical shell. Outside the spherical shell. So this is a spherical shell of mass capital M and radius capital R, and we are taking the point mass distance r from the center. The mass of the particle is m. The gravitational force according to universal law of gravitation is g capital M small m by r square. Here r will be greater than capital R. So in this, f inversely proportional to r square is there. and case 2 we have got it here. So if the point mass again is taken inside the shell, lies inside this shell, so again we consider spherical shell, a radius r, and a particle is taken inside the spherical shell, a distance r, and the gravitational force between them is 0. There's an important point here. It is r will be less than, small r will be less than capital R. And if you aim for the graph between the F and R, so inside region there is no graph, and outside region we have rectangular hyperbola. So because inside the force is 0 and outside we have inversely proportional to r square, and you get rectangular hyperbola graph here for outside region.